Hi there! Let's begin with this super interesting chapter, Structure of the Atom. We know that atoms and molecules are the fundamental building blocks of matter. There are so many different kinds of matter in this world. The existence of different kinds of matter is due to different atoms constituting them. However, some questions that arise are: what makes the atom of one element different from the atom of another element? And are atoms really indivisible as proposed by Dalton, or are there smaller constituents inside them? We shall find out the answers to these questions in this chapter. We will learn about subatomic particles and the various models that have been proposed to explain how these particles are arranged within the atom. One of the first indications that atoms are not indivisible comes from studying static electricity and the condition under which electricity is conducted by different substances. Charged particles in matter. For understanding the nature of charged particles in matter, let us carry out some activities. Comb dry hair. Now, does the comb then attract small pieces of paper? Rub a glass rod with a silk cloth and bring the rod near an inflated balloon. Observe what happens. These activities show that on rubbing two objects together, they become electrically charged. Where does this charge come from? This question can be answered by knowing that an atom is divisible and consists of charged particles. Many scientists contributed in revealing the presence of charged particle in an atom. It was known by 1900 that the atom was indivisible particle but contained at least one subatomic particle. The electron, identified by J. Thomson. Even before the electron was identified, E. Goldstein in 1886 discovered the presence of new radiations in a gas discharge and called them canal rays. These rays were positively charged radiations, which ultimately led to the discovery of another subatomic particle. This subatomic particle had a charge, equal in magnitude but opposite in sign to that of the electron. Its mass was approximately 2000 times as that of electron. It was given the name of proton. In general, an electron is represented as E- and a proton as P+. The mass of a proton is taken as 1 unit and its charge as +1. The mass of an electron is considered to be negligible and its charge is -1. It seemed that an atom was composed of protons and electrons, mutually balancing their charges. It also appeared that the protons were in the interior of the atom, for whereas electrons could easily be removed off, but not protons. Now, let's discuss a scenario where an atom contains one electron and one proton. Do you think it will carry any charge or not? We already have known that an electron has an opposite charge to that of proton, and also the magnitude of the charge is equal. As a result, if the atoms have one electron and one proton, then that atom will be electrically neutral. This means that the atoms will carry no charge as they are neutral. Therefore, if an atom contains one electron and one proton, it will carry no charge. The structure of an atom. We have learned Dalton's atomic theory in chapter 3, which suggested that the atom was indivisible and indestructible. But the discovery of two fundamental particles, electrons and protons, inside the atom led to the failure of this aspect of Dalton's atomic theory. It was then considered necessary to know how electrons and protons are arranged within an atom. For explaining this, many scientists proposed various atomic models. Joseph John Thomson was the first one to propose a model for the structure of an atom. J.J. Thomson was a British physicist, and he was born in Cheetham Hill, a suburb of Manchester, on 18 December 1856. He was awarded the Nobel Prize in Physics in 1906 for his work on the discovery of electrons. He directed the Cavendish Laboratory at Cambridge for 35 years, and 7 of his research assistants subsequently won Nobel Prizes. Thomson's model of an atom. Thomson proposed the model of an atom to be similar to that of a Christmas pudding. The electrons in a sphere of positive charge were like dry fruits in a spherical Christmas pudding. We can also think of a watermelon. The positive charge in the atom is spread all over like the red edible part of the watermelon, while the electrons are studded in the positively charged sphere, like the seeds in the watermelon. Thomson proposed that an atom consists of a positively charged sphere and the electrons are embedded in it. The negative and positive charges are equal in magnitude. So, the atom as a whole is electrically neutral. Although Thomson's model explained that atoms are electrically neutral, but the result of experiments carried out by other scientists could not be explained by this model. Don't forget to subscribe to the channel and hit the like button. A comment from you would make our day brighter. Rutherford's model of an atom. Ernest Rutherford was interested in knowing how the electrons are arranged within an atom. Rutherford designed an experiment for this. In this experiment, fast-moving alpha particles were made to fall on a thin gold foil. Why gold foil? Because he wanted a layer as thin as possible. This gold foil was about 1000 atoms thick. What are alpha particles? Well, these are doubly charged helium ions. Since they have a mass of 4u, the fast-moving alpha particles have a considerable amount of energy. It was expected that alpha particles would be deflected by the subatomic particles in the gold atoms. Since the alpha particles were much heavier than the protons, he did not expect to see large deflections. But the alpha particle scattering experiment gave totally unexpected results. The observations made were: most of the fast-moving alpha particles passed straight through the gold foil. Some of the alpha particles were deflected by the foil by small angles. Surprisingly, 1 out of every 12,000 particles appeared to rebound. In the words of Rutherford, this result was almost as incredible as if you fire a 15-inch shell at a piece of tissue paper and it comes back and hit you. Before moving on to the implications of this experiment, let's get to know some basic details about this scientist. E. Rutherford was born at Spring Grove on 30th August 1871. He was known as the father of nuclear physics. He is famous for his work on radioactivity and the discovery of the nucleus of an atom with the gold foil experiment. He got the Nobel Prize in Chemistry in 1908. Getting back to the gold foil experiment now. Let us think of an activity in an open field to understand the implications of this experiment. Imagine a child in front of a wall with her eyes closed. Let her throw stones at the wall from a distance. She will hear a sound when each stone strikes the wall. If she repeats this 10 times, she will hear the sound 10 times. But if a blindfolded child were to throw stones at a barbed wire fence, most of the stones would not hit the fencing and no sound would be heard. This is because there are lots of gaps in the fence which allow the stone to pass through them. Following a similar reasoning, Rutherford concluded from the alpha particle scattering experiment that most of the space inside the atom is empty. Why? Because most of the alpha particles pass through the gold foil without getting deflected. Very few particles were deflected from their path, right? This indicates that the positive charge of the atom occupies very little space. A very small fraction of alpha particles were deflected by 180 degrees, which indicates that all the positive charge and mass of the gold atom were concentrated in a very small volume within the atom. What do you think would be the observation if the alpha particle scattering experiment is carried out using a foil of a metal other than gold? If it is carried out using a foil of any other metal, there would be no change in observations if the foil is as thin as the gold foil used here. But since other metals are not so malleable, so such a thin foil is difficult to obtain. If we use a thick foil, then more alpha particles would rebound. Now, from the data, Rutherford also calculated that the radius of the nucleus is about 10 raised to the power 5 times less than the radius of the atom. On the basis of his experiment, Rutherford put forward the nuclear model of an atom, which had the following features. There is positively charged center in an atom called the nucleus. Nearly all the mass of an atom resides in the nucleus. The electrons revolve around the nucleus in circular paths. The size of the nucleus is very small as compared to the size of the atom. Let's see the drawbacks of Rutherford's model of the atom. The revolution of this electron in a circular orbit is not expected to be stable. Any particle in a circular orbit would undergo acceleration. During acceleration, charged particles would radiate energy. Thus, the revolving electron would lose energy and finally fall into the nucleus. If this was so, the atom would be highly unstable and hence matter would not exist in the form that we know. We know that the atoms are quite stable. In order to overcome the objections raised against Rutherford's model of an atom, Niels Bohr put forward some postulates about the model of an atom. Let's first get to know the man. Niels Bohr was born in Copenhagen on 7th October 1885. He was appointed professor of physics at Copenhagen University in 1916. He got the Nobel Prize for his work on the structure of atom in 1922. Among Professor Bohr's numerous writings, some notable books are The Theory of Spectra and Atomic Constitution, Atomic Theory and the Description of Nature. Let's discuss Niels Bohr's postulates now. Only certain special orbits known as discrete orbits of electrons are allowed inside the atom. While revolving in discrete orbits, the electrons do not radiate any energy. These orbits or shells are called energy levels. Energy levels in an atom are shown in the figure here. These orbits or shells are represented by the letters K, L, M, N or the numbers 1, 2, 3, 4. If you're liking the video, don't forget to hit the like button and subscribe to the channel. Neutrons. In 1932, J. Chadwick discovered another subatomic particle which had no charge and a mass nearly equal to that of a proton. It was eventually named as neutron. Neutrons are present in the nucleus of all atoms, except hydrogen. Therefore, an atom has three subatomic particles, namely electron, proton, and neutron. In general, a neutron is represented as N. The mass of an atom is therefore given by the sum of the masses of protons and neutrons present in the nucleus. Let's see an example. Helium atom has an atomic mass of 4U and 2 protons in its nucleus. How many neutrons does it have? Number of protons plus number of neutrons gives us the number of electrons, which is also equal to the mass number. The mass number of helium is 4 and the number of protons in helium is 2. Therefore, number of protons plus number of neutrons we know is mass number, which gives us number of neutrons to be 2. Therefore, number of neutrons in helium atom are 2. How are electrons distributed in different orbits or shells? The distribution of electrons into different orbits of an atom was suggested by Bohr and Bury. Rules followed for writing the number of electrons in different energy levels or shells are: the maximum number of electrons present in a shell is given by the formula 2n square, where n is the orbit number or energy level index 1, 2 or 3, etc. Hence, the maximum number of electrons in different shells are: first orbit or K shell will be 2, second orbit or L shell would be 8, third orbit or M shell would be 18, fourth would be 32, and so on. The maximum number of electrons that can be accommodated in the outermost orbit is 8. Electrons are not accommodated in a given shell unless the inner shells are filled. That is, the shells are filled in a stepwise manner. Here is the atomic structure of the first 6 elements. And here is the atomic structure of the next 12 elements. Out of the given 18 elements, let's discuss the distribution of electrons in carbon and sodium atoms. The atomic number of carbon is 6. The first 2 electrons are in the first orbit or K shell. The next 4 electrons are in the second orbit or L shell. Hence, the electronic configuration is 2, 4. The atomic number of sodium is 11. The first 2 electrons are in the first orbit, the next 8 electrons are in the second orbit, and the remaining 1 is in the third orbit. Hence, the electronic configuration is 2, 8, 1. Interesting, isn't it? Now consider this. If K and L shells of an atom are full, then what would be the total number of electrons in an atom? The maximum number of electrons that can be occupied in the K and L shells of an atom are 2 and 8 respectively. Therefore, if the K and L shells of an atom are full, then the total number of electrons in the atom would be 2 plus 8, that is 10 electrons. Valency. The electrons present in the outermost shell of an atom are known as the valence electrons. From the Bohr-Bury scheme, we also know that the outermost shell of an atom can accommodate a maximum of 8 electrons. It was observed that the atoms of the elements completely filled with 8 electrons in the outermost shell show little chemical activity. In other words, their combining capacity or valency is 0. Of these inert elements, the helium atom has 2 electrons in its outermost shell, and all other elements have atoms with 8 electrons in the outermost shell. The combining capacity of the atoms of elements, that is, their tendency to react and form molecules with atoms of the same or different elements, was thus explained as an attempt to attain a fully filled outermost shell. An outermost shell which had 8 electrons was said to possess an octet. Atoms would thus react so as to achieve an octet in the outermost shell. This was done by sharing, gaining, or losing electrons. The number of electrons gained, lost, or shared so as to make the octet of the electrons in the outermost shell gives us directly the combining capacity of the element, that is, the valency. For example, hydrogen, lithium, sodium atoms contain 1 electron each in their outermost shell. Therefore, each one of them can lose 1 electron. So, they are said to have valency of 1. Similarly, magnesium has 2 electrons in its outermost shell, and aluminium has 3 electrons in its outermost shell. Therefore, valency of magnesium and aluminium is 2 and 3 respectively. If the number of electrons in the outermost shell of an atom of an element is less than or equal to 4, then the valency of an element is equal to the number of electrons in the outermost shell. However, if it is greater than 4, then the valence is determined by subtracting the outermost shell of the electrons from 8. For example, the fluorine atom has 7 electrons in the outermost shell, and its valency could be 7, but it is easier for fluorine to gain 1 electron instead of losing 7 electrons, right? Hence, its valency is determined by subtracting 7 electrons from the octet, and this gives you a valency of 1 for fluorine. Valency can be calculated in a similar manner for oxygen. What is the valency of oxygen that you get from this calculation? Well, atomic number of oxygen is 8, so electronic configuration is 2, 6. Therefore, the valency is 8 minus 6, which gives us 2. Let's find the valency of chlorine. Atomic number of chlorine is 17. Therefore, the configuration would be 2, 8 and 7. Now it is easier for chlorine to gain 1 atom instead of losing 7. Gain 1 electron instead of losing 7. Therefore, the valency of chlorine would be 8 minus 7, which is 1. Let's find the valency of sulfur now. Atomic number of sulfur is 16. Electronic configuration therefore is 2, 8 and 6. The valency of sulfur would be 8 minus 6, which is 2. Let's find the valency of magnesium. The atomic number is 12, electronic configuration is 282. Therefore, the valency would be 2. Therefore, an atom of each element has a definite combining capacity called its valency. Here is the valency of the first 18 elements. Hope you're liking the video. In that case, don't forget to subscribe to the channel and hit the like button. Atomic number and mass number. Let's first discuss the atomic number. We know that protons are present in the nucleus of an atom. It is the number of protons of an atom which determines its atomic number. It is denoted by Z. All atoms of an element have the same atomic number, Z. In fact, elements are defined by the number of protons they possess. For hydrogen, Z is 1 because in hydrogen atom, only one proton is present in the nucleus. Similarly, for carbon, Z is 6. Therefore, the atomic number is defined as the total number of protons present in the nucleus of an atom. Mass number. After studying the properties of the subatomic particles of an atom, we can conclude that mass of an atom is practically due to protons and neutrons alone. These are present in the nucleus of an atom. Hence, protons and neutrons are also called nucleons. Therefore, the mass of an atom resides in its nucleus. For example, mass of carbon is 12U because it has 6 protons and 6 neutrons. Similarly, the mass of aluminum is 27U. It has 13 protons and 14 neutrons. The mass number is defined as the sum of the total number of protons and neutrons present in the nucleus of an atom. It is denoted by A. In the notation for an atom, the atomic number, mass number, and symbol of the element are to be written as shown here. Mass number, symbol of element, and then atomic number. Let's try this. If number of electrons in an atom is 8 and number of protons is also 8, then what is the atomic number of the atom and what is the charge on the atom? Since number of protons is equal to the number of electrons, that is 8, therefore charge on the atom is 0. Next is isotopes. In nature, a number of atoms of some elements have been identified which have same atomic number but different mass numbers. For example, take the case of hydrogen atom. It has 3 atomic species, namely protium, deuterium, and tritium. The atomic number of each is 1, but the mass number is 1, 2, and 3 respectively. Other such examples are carbon and chlorine. Chlorine occurs in nature in 2 isotopic forms with masses 35U and 37U in the ratio of 3:1. Obviously, the question arises, what should we take as the mass of chlorine atom? Let us find out. Knowing that out of 2 isotopes of chlorine, 75% availability is that of one with mass 35U and the rest is the one with mass 37U, the average atomic mass of chlorine atom will be 35 into 75 by 100 plus 37 into 25 by 100, which gives us 35.5 U. This does not mean that any one atom of chlorine has a fractional mass of 35.5 U. It means that if you take a certain amount of chlorine, it will contain both isotopes of chlorine and the average mass is 35.5 U. The mass of an atom of any natural element is taken as the average mass of all the naturally occurring atoms of that element. If an element has no isotopes, then the mass of its atom would be the same as the number of protons and neutrons in it. But if an element occurs in isotopic forms, then we have to know the percentage of each isotopic form and then the average mass is calculated. Many elements consist of a mixture of isotopes. Each isotope of an element is a pure substance. The chemical properties of isotopes are similar, but their physical properties are different. Let's see the applications of isotopes. Since the chemical properties of all the isotopes of an element are the same, normally taking a mixture is not a concern. But some isotopes have special properties which find them useful in various fields. Some of them are: an isotope of uranium is used as a fuel in nuclear reactors. An isotope of cobalt is used in the treatment of cancer. An isotope of iodine is used in the treatment of goiter. Isobars. Atoms of different elements with different atomic numbers which have the same mass number are known as isobars. Let us consider two elements, calcium, which has an atomic number of 20, and argon, which has an atomic number of 18. The number of protons in these atoms is different, but the mass number of both these elements is 40. That is, the total number of nucleons is the same in the atoms of this pair of elements. Congratulations, you just finished this chapter. How about some little fun at the end? A neutron walks into a bar and asks, "How much for a drink?" The bartender replies, "For you, no charge." Have a good one, guys. Hope you liked the video. Do write your feedback in the comment section below and hit the like button. Share it with your friends and family. Stay healthy, stay happy, stay kind, make healthier choices, and keep watching IC Kids. Subscribe to the channel and don't forget to hit the bell icon. Goodbye.